Okay, Steve, are you ready? We can get started.
I am ready.
Okay. Welcome, everybody. Dr. Stephen Conley, he is joining us from Boulder, not far away from my hometown of Denver. So he is with us here today virtually. And so wanted to give you a little background on everything Steve has done. Dr. Stephen Conley is a pioneer in atmospheric sampling of greenhouse gases and pollutants from research aircraft. After completing his BS in physics, he worked as a software developer for IBM, as a naval electronics officer training aboard a guided missile frigate, and started a software company, as well as obtaining his private pilot's license years ago. In 2003, he encountered every pilot's worst nightmare, flying at night into a severe thunderstorm. Aviating safely through extreme turbulence sparked a newfound interest in the physics of atmosphere, and Steve went on to earn a PhD in atmospheric science from the University of California, Davis. Steve founded Scientific Aviation after graduation in 2010, while continuing to work at UC Davis as a project scientist and postdoctoral scholar. Scientific Aviation combines Steve's talents and interests in aviation, atmospheric sciences, and computer programming. His company now owns several scientifically instrumented Mooney aircraft and drones that have flown around the US and throughout the world, studying emissions, chemistry, and meteorology of atmospheric boundary layers. In 2015, Steve carried out over a dozen flights to measure and quantify the Aliso Canyon disaster, a month-long uncontrolled release of methane and other gases from a failed well pad in LA that sickened thousands and drove many from their homes. His real-time observations provided uniquely accurate information on emission rates, chemical composition, and the effectiveness of well control measures. Steve's observations documented the evolution of the largest accidental release of methane in U.S. history. His work was published in Science, and the data, since independently confirmed, has guided remediation and settlement efforts throughout into the present day. Most recently, Steve has pioneered a novel hardware and software solution to provide continuous off-grid monitoring of methane emissions from oil and gas production and distribution facilities. The Systematic Observations of Facility Intermittent Emissions, or SUFI. SUFI is designed to reduce methane emissions by providing reliable, cost-effective, automated information on methane leak rates to improve leak detection and repair, LDAR, efficiency. This invention now extends scientific aviation coverage from the sky down to the ground and provides improved operational awareness for clients in the energy industry. And Steve, with that, I am done chatting about you, and it's all yours.
I should have pre-read that. I didn't realize that intro was so chatty. Sorry, everybody. But yeah, my background has been since the early 2000s in looking at different methane emissions, and originally looking at it just from the air, from actually manned aircraft, and then ultimately down to drones, and then finally onto the fixed ground-based sensors. So the one thing that I have come to learn over the years is that there really is no silver bullet solution for detecting methane. It really, you have to sort of start with the question that you're asking, because different questions will have different answers. So different technologies are better depending on what it is that you're trying to accomplish. So yeah, I guess I can skip this. The photo here is, we take these aircraft all over the world. And so this was, we were doing some United Nations flights in the Norwegian North Sea. And so we took one of these planes over to Norway for a month to do these flights. And so that was the exciting moment when we landed on the European continent and kind of felt like we'd made it. It was our first time ever taking one of these Moonies out over the ocean. Well, I should say that far over the ocean. So the leak that we were talking about in the introduction, the Aliso Canyon disaster, is shown here on a thermal infrared image. And what you see is this really dramatic image of what the leak looked like. But what it left behind was one big question. Is this a lot or a little? And this was the position that the state of California found themselves in back in November of 2015, that on the one side, they had the local residents who were convinced that the sky was falling. This was the greatest disaster in history. And on the other side, they had the local operator who thought it was nothing unusual. And this bickering went back and forth for 2 weeks until the state finally sent one of our aircraft down with one objective, which was to put a number on this. Like, how big is this? What response would it dictate? And that first measurement that we took, which was about 60 tons per hour, was what led to the state declaring a state of emergency and evacuating something like 8,000 residents. But to get to that, what you had to do was convert this from this image or a ppm level to an actual emission rate. And so that's where scientific aviation has focused since the beginning. Since the first flight we ever did, our job has always been around this goal of putting a number on it, quantification, as we now call it. So we use 3 different techniques to find emissions, specifically of methane, but other gases as well. The one that we have the most time with is obviously the manned aircraft, where you have many thousands of hours of flights using the manned aircraft. And when I talk about how each of these techniques and others, not just the ones that we offer, but other techniques as well, how they all fit into this sort of greater solution, I kind of like will tell you as we go through these where each of these techniques fits well. So for example, the manned aircraft have one huge strength. They can cover a lot of ground. So with a manned aircraft, you can cover something like 1,000 square miles in a day. So like a typical use of the aircraft would be if you wanted to survey an entire basin and you wanted to know where are my super emitters and you wanted to know fast. The airplane is a great tool for that. The thing that's nice about the aircraft is that speed means it can get to places in a hurry. So let's say you have some event that pops up today in Champaign, Illinois. We can get a plane anywhere in the continental US in a few hours. And so wherever the problem happens, the plane can get there quickly, which is why it was so useful with that Aliso Canyon disaster, who's able to be there 2 hours after we were given the go order. So the one final thing that the airplane can do that is really difficult or actually impossible with any other technique is the airplane can quantify emissions from an entire basin. And so sometimes that's been useful when we're trying to compare top-down and bottom-up methods, that oftentimes we found that, like when we use the inventory methods, you can't just go measure one site to compare, because you might hit that one site on a day when it's high or low, when something's going on or it's shut off. Whereas if you sample an entire area with thousands of sites, you're going to get a good statistical average. And so the airplane can do a really nice job of that it can encircle an entire area and in the end, give you an emission rate for that area. The next one down is the unmanned aircraft, or the drones. The strength of the drone is that while the aircraft is going to fly like in the tightest circle it can turn is about 1 kilometer. And so if you imagine the Permian Basin, in that 1 kilometer circle, there might be more than one site. And so with the aircraft, depending on where you're flying, you may not be able to get as precise as you want when you're looking at which site has the emission problem. The drone, on the other hand, can turn as tight a circle as we want. It can stop and hover. So the drone can do 2 things better than the aircraft. One of them is where the aircraft is going to see leaks that are approaching the super emitter. So just for spectrum here, the super emitters are said to start at 25 kilograms per hour or so. The airplane reliably will see 10 kilograms per hour. By comparison, the drone's about 1,000 times more precise. It'll see, instead of 10 kilograms, 10 grams per hour. So the drone is the most accurate tool for quantifying an individual site measurement. And that's whether it's our drone or somebody else's. It just is, because the drone can actually fly this beautiful curtain downwind of a site. And so it can actually capture all the methane leaving the site. So it is the most accurate means of doing a full site quantification, like if you're trying to calculate methane intensity, for example. But the other thing that's nice about the drone is that when it compared with the airplane, it's much, much more precise at pinpointing where the source is. So where the airplane is going to give you a sort of uncertainty of a couple 100 meters, the drone is closer to 1 meter. So you get a much better idea of where your problem is. The drone still can't match the camera, and that the OGI camera can actually give you an image of where it's coming from. So it'll actually tell you what bolt or valve you need to tighten, which is an advantage of the camera. But by comparison, the drone is order of magnitude faster than the camera. And then the third thing is the continuous monitoring. And so the place that this is important is all of the other techniques that I talk about today, whether it's satellites, planes, drones, these are all point in time measurements. And so you always have that question of, well, what if something happens the day after I go visit? And that's a real problem, because some of these super emitters that we discover are in the thousands of kilograms per hour. And so the whole objective is to reduce the amount of time that those are running. And so when you do the point in time measurements, the question is, it becomes this cost versus benefit. How often can I go and be often enough? Like every time I go, it costs money. And so I don't want to go too often, but then if I don't go often enough, one of these super emitters could run for months or more. So that's where the continuous monitoring tends to have its advantage, that it is the most cost-effective tool if you want to rapidly identify super emitters. So you're going to find out about those within minutes instead of weeks or months or even years. The other thing that the continuous monitoring can do, because it's measuring this continuously as the wind changes, it lets you triangulate to where the sources are. So the continuous monitoring system doesn't just blindly give you a leak notification, it can also tell you where it's coming from. So that's another benefit of the continuous monitoring. So this is just, I'm not going to get too sciencey on you here, but this is basically the idea of how the methodology works. And it's actually, for all of our tools, it's effectively the same. I'll kind of explain the differences when the continuous monitoring once I sort of walk through this. But if you look at the sort of image on the left here, where you see an aircraft circling like what would be a ground source, the idea here is that the aircraft constructs this closed cylinder around it, like imagine a coffee can being put over it. And then what's happening here is the wind, which is shown here blowing from left to right, is blowing this plume of gas as it rises down through the downwind side of this cylinder. And so what happens here as the plane circles, it just has to add up the amount of methane that's coming into our cylinder and the amount that's leaving. And the difference, this is just from your continuity of mass, the difference here is what came from the source. And so both the method for calculating the wind from the aircraft and for using this Gauss's theorem to calculate the emission rate were both published at Scientific Aviation in the peer-reviewed literature. And these techniques are now used both by NOAA and NASA. So they're very well vetted now, but we did publish them. This was the creation at Scientific Aviation. On the right here, you see two examples of real flights. So this top one is the McDonald Island Storage Facility in Sacramento. And you see the bold white arrow is showing the wind direction. And as you'd expect, on the downwind side, you see these the colors indicating higher levels of methane. And so the way we can sort of judge a flight's success is that, first of all, I want to see that I get a nice clean signal so that the leak is big enough that the airplane can see it, which it is here. And then second, I want to see if the airplane got high enough. And in this case, if I look at the top two legs, I just see blue, meaning that we got above the plume. And that's important. And as we saw over here, that the plane has to get high enough to capture the entire vertical extent of the plume. And that's the same for the drone. And so if I look down the bottom here, this is an LNG facility in Australia, and this is a drone flight. And similarly, you see that in this case, instead of the circles, the drone is doing a just downwind transects. But similarly, you see the high levels of methane on the downwind side of the tank. And so just like we do with the circles, we can add up all the methane that's passing through this curtain that we build. And from that, we can calculate that leak rate as we showed here. And then the one thing I was going to say about the continuous system is it's largely similar with one big exception, where the plane and the drone can fly through the plume. With the continuous system, it sits still and we assume wind direction bring the plume to us. And so that's a pretty big assumption, because if the wind doesn't turn towards you, then the continuous monitoring system or fixed monitors can just miss the emission. And so one thing you have to know about continuous monitoring is that it's a bit of a waiting game. The more sensors you have, the more quickly you'll see an emission. And I'll talk a little bit about Project Falcon, where we did these studies with a bunch of different operators to figure out what the optimal number of sensors on a facility is. And that, just to give you a hint, it all comes down to how long are you willing to wait to find out about an emission. So this is just showing you what is capable with the aircraft. So all of our aircraft look the same, basically. Out on the right wing here, outside of the prop wash and the exhaust, we have what looks like these little air inlets of different materials so that we can measure different gases. But what's happening is all of these have lines that go through the wing and they terminate in the baggage area. And then to that, we can connect whatever instruments we want for a given project. We pretty much always fly with a Picarro greenhouse gas analyzer. That is the sort of global standard for for methane measurements. And so then based on that, the planes can measure the wind. That was the method I showed on the previous slide. And we combine that with the location and the methane. That's how we are able to sort of measure and calculate these leak rates. And by the way, the drone has to have the same things. So the same requirements exist, whether it's the drone or the plane. So the question we always get is, how do I know that this plane flying through this invisible cloud is actually meaningful? How do I know it works? And the Aliso Canyon disaster ended up being what I would say was the most public method validation in history. Because it was so big, it affected so many people. There was scrutiny on this from every side. So the operator hired experts, NASA was there. In fact, for a year, we had NASA telling the world that the numbers that we were reporting were wrong. And so it was an ugly year for me to be defending it. But luckily, after 13 months, when NASA released their official estimates, they were within 3% of what we had released before the plane landed. And that was a moment that really changed the course of scientific aviation from sort of generic atmospheric research to specifically methane. Because what became clear that day was these flights that cost $8,000 in the plane ended up being just as accurate as the $100 million NASA system, and they gave results in minutes instead of months. So, but this kind of shows these little white circles here are the measurements that the airplane took. And then all the other ones are measurements that other group like NASA and the Aerodyne was there doing measurements with trace and release. And so all these other measurements are what other people did over time. And you just kind of see how they're overlaid and how well they match what the airplane did. And then in the end, like I said, the all three for the total were really close. So NASA was 3% more than us, Aerodyne was 11% less, and even SoCalGas's own inventory was within 13%. So then moving on to the unmanned aircraft. So keeping in mind the purpose of the unmanned aircraft is not to save cost, because it actually ends up being more expensive because it can cover so many fewer sites in a day, but it's because it gives you much greater precision, so that the drone can actually get in and measure the smallest of leaks and do a really good job of pinpointing the source. And so in this case, we're flying with canisters as well as the methane measurement. And with the canisters, the nice thing that we can do with them is if we ever want to identify what's in an emitting gas, we can do that. So we've had that request to like sample what's in the flares or what's coming out of the compressors. And so with the drone, you can use the real-time methane measurement to sort of drive it into the plume and then trigger an air sample once you're in the plume that we can then send off to be analyzed for hundreds of different gases. But the big thing about the drone is that really similar to the airplane. In fact, the drone uses the exact same software to do the methane quantification. But with the drone, that you can actually take these measurements and sort of get in close enough that that signal to noise ratio the plane sees doesn't become a problem anymore, so that really small leaks, in fact, with the drone, smaller leaks than you can see with an OGI camera will be obvious on the drone. So that's its claim to fame, I guess I would say. If you're looking for the real small leaks, or you just want to do a survey more quickly, that's when the drone is useful. And this just shows sort of our first controlled release test with the drone. So the big question with the drone when we first built it was, how accurate would it be? And so what we did is we set up a controlled release at Boulder Airport, where our office is. And that's this image on the left here is showing the tank and the flow meter. And so we flew the drone around this emission for about 5 minutes. But the exciting thing was that we were releasing 41 grams per hour, and then in 5 minutes, the drone estimated 37 grams per hour. So it was within 10% of the actual release rate. And this is what I think is the drone's strength, that in 5 minutes, like the plane to do a typical quantification is closer to 20 minutes, and the drone did this in 5. And so for actually going to an individual facility and doing a really detailed measurement, the drone is sort of tough to beat. And then this video here is just kind of shows what you see. So this image here is what is on the drone, so, or on the remote controller that the pilot's using. So this is what you're seeing in real time. And the red line here is the methane concentration, and then you get this image of what the drone is seeing from the camera. And so what you see here is that, as in this case, this tank number 1 here has an emission. And you see as you get downwind of it, you get this really unmistakable signal. And this is one of the strengths of the drone, is that if any of you have used the OGI camera, sometimes when you're looking at the camera image and you're sort of seeing this black cloud, like I showed in that first image, it's not always obvious. And so it means that if you want to look for small leaks, what you really have to do is stop and scrutinize each potential leak source. You can't just scan. Scanning works for large emissions, not for small. Whereas with the drone, a leak of 10 grams per hour, you still see a really clear signal like this. And so it's something that doesn't require thousands of hours of experience for someone to be able to do. Like, once somebody understands how to fly, which, you know, getting a licensed drone pilot takes about 40 hours. But at that point, someone is qualified to do a flight like this. And so that's one of the strengths. And we found this when we were flying in Ukraine for the European Bank. Then we went with a camera crew. And what we learned was that on one of these giant underground facilities that we were measuring, they were like a kilometer on a side. What we found is that the camera crew would take an entire day to survey it, where the drone could do it in 10 minutes. So what we ended up discovering by the end of the week was that a much better use of our time was to have the drone go do the rapid survey and then just point the camera to the 3 areas we found problems. And then the camera could go do a much better job than the drone of actually pinpointing the issue. So this is coming on now to the last thing I want to talk about, which is the continuous monitoring. And so this example shows, this is a flight that we were doing on the Permian map project last year. And we just sort of stumbled across this emission. And now, obviously, as you can see, it's big enough that it actually shows up on the visual image. And it turned out that that leak was about 12 tons per hour, or 1.3% of the US oil and gas total. And so when people talk about the super-emitter problem, like, this is what we're talking about. That one out of 1.5 million wells, one site is bringing up 1.3% of the total. And so when you think about the math here, that if you want to know what's your total emission, you take your emission rate times the amount of time it's running for. And so the one reality that I think we all have to be sort of practical about is that you can't stop leaks from happening. So you can do a better job of maintaining, have newer equipment, and you can certainly reduce the frequency of failures, but you can't stop them. The one thing that you can control is this other term here, which is the duration. And so that's where continuous monitoring comes in. It's all about shortening that duration that these super emitters are running for. And obviously 12 tons per hour is a big example, but still a 25 kilogram per hour is something that we want to pay attention to. And so that's where with continuous monitoring, like something like this, any continuous monitoring system would have discovered this within minutes. And so as it was, when the plane found it, it still took 3 days before we got to the right people on the ground to figure out who owned it, to get trucks out there and actually fix it. So we don't know how long this ran before the plane got there, but we do know that once we got there, it still took 3 days to fix it. And that's where if someone had had a continuous monitoring system here, this would have probably been fixed in a few hours. So that's what we're after here with continuous monitoring. And you think about like the EPA talking this year about how to change the regulations to better deal with these super emitters. And like, do you take more visits with cameras? And well, that's got some trade-offs, because first of all, like the EPA estimates that every OGI visit is something like $500. And so if you want to go weekly or monthly, you've got to think about the cost. But then not just cost, but the fact that those big trucks driving around are now, basically trading CH4 for CO2, right? All these vehicle miles don't come free. And the other thing is just the safety, that driving is like a major source of injury to people in the Permian. And so if we can reduce the number of vehicle miles, that only helps too. And so the idea with continuous monitoring is, instead of just going out to a site to find nothing, you go out to a site when something is happening. And that's what we're sort of after. So when we talk about how each of these technologies fits, continuous monitoring is really good for that. So this is showing sort of the spectrum of what's available in this leak detection space. And so starting at the top of the atmosphere, you have the satellite systems. And depending on whose you look at, their detection limit demonstrated is somewhere on the order of 200 kilograms per hour. And then, when you're getting imagery, it's something like $25 per site. And obviously these numbers all change based on the density and what agreement you have, but something like that. EDF is launching a satellite that'll be free, but it'll have a higher detection limit and sort of lower precision. And then moving down from the satellites, the next sort of level coming down vertically is aircraft. And the detection limit goes down a bunch, 200 to 10, but there's a big caveat. Satellites can work anywhere. They need clear skies. So maybe there's places that are out in the middle of nowhere that would be impractical or too costly to send a plane to, because that price is dependent on you having an aircraft nearby. Or maybe it's a war zone. So there's plenty of reasons that you don't want to necessarily send an airplane. And for those situations, a satellite wins. If airplane is there, then I would say, given the cost and the detection limit, an airplane beats the satellite if the two can both work the same area. And then moving down from the plane, you come down to the drones. And like I said before, your detection limit gets 1,000 times better, but your cost goes up by a factor of 10. So because the drone is dependent on driving from site to site, it ends up being a lot more expensive. But for that money, you get a better detection limit and better sort of location of where problems are. And then coming down to the last level here, walking around with a camera, similar detection level to the drone, cost goes up just because it's so much slower, but you also lose the ability to quantify. So if the goal is quantification, then the camera is not the right solution. But if the goal is to fix these small leaks, the camera wins because it actually gives you a picture of where the leak is, so you know exactly what the problem is. And then all of these we qualify as these point-in-time measurements. And then moving over to the right side here, something like the continuous monitoring systems. And these are basically, I put a cost here for comparison purposes, but the continuous monitoring is going to detect something in that 1 kilogram per hour range. So it's better than the plane, but not as good as the drone. But it's not a point-in-time measurement. So it's going to be watching continuously. So that's really nice because, like we said, that when you have an event, the continuous monitoring system knows about it right away. It's also good for the opposite, for identifying when you did not have an event. So we've seen that used, that neighbors complain about odor or something like that, and it's nice to be able to show with data that there wasn't a leak coming from this site at that point. So that's one advantage of the continuous monitoring. And so this is now specifically about our system and just how it works. And, basically these are about $1,500 each. And the idea with these is that they're always focused, just like the other technologies we make, on the leak rate as opposed to the concentration. And I'm going to show you why on the next slide. Another thing that they do, like I mentioned, is this ability to triangulate. And so that means that they don't just generically send you out to a site. They send you to a site and then give you an idea of where the emission source is. So the idea with this is, why have we always focused on emission rate? So when we first started doing SUFI, we were the only ones that used emission rate. And I've seen now a lot of our competitors are now adding emission rate quantification to their products. But the reason that we've always done it is what's shown right here. And in this case, this is our in week off our dashboard, and the solid or the shaded blue line here is the wind speed. And then the other 4 lines are methane sensors on this facility. And so what I want you to notice is every time the wind stops, look what happens to the concentration, right? Wind goes low, methane goes high. Wind goes low, methane goes high. And so what that means is that if you're basing your alerts on the concentration level, then you're going to get all these false alarms that are just based on changes in the atmosphere. And that might be, like in this case, the wind stopping or the atmospheric boundary layer collapsing like it does every night. But you're getting alerts that are based on atmospheric changes and not leak changes. And so because of that, we've always argued that the only proper metric here is to actually combine the methane with the wind, with the atmospheric stability and the pressure, the temperature, and actually running this through a plume model to come up with an emission rate. Because when the emission rate goes high, there really is an event on the site. And the only problem is we still can't tell you whether that event is an intentional event, like a maintenance event, or an unintentional event. We haven't been able to get to that yet. But at least we can tell you that that event is not just a change in the wind, that the event that we're reporting to you is actually methane being released. So this is an example of that triangulation I was talking about. So in fact, this was the very first site that we ever set up. And in this case, it's a central processing facility, and we have 4 sensors on it. One here, one here, one here, and there's one that's off the map down here. So we're monitoring this facility. And then to the north was another site, just a well pad owned by that same operator. And so with these first sensors, what happened is on one evening, sensor number 1 picks up an emission at 6 p.m. Winds are coming out of the east. And then 3 hours later, sensor 3 picks it up with winds out of the northeast. And so it generated an alert, but for the flare on the adjacent facility. And so, given that was the very first sensor doing this, everybody kind of suspected it was an error. And when the repair crew called us from the site to report that indeed the flare was out, it was a really exciting moment for 2 reasons. Obviously, one was that the system worked, but number 2 is it pointed out to us something we hadn't thought about, which was that sensors don't need to belong to a site. So these sensors are on this border between the 2. If the wind's coming from the north, they're protecting this site. If it's coming from the south, they're protecting this site. And so it's a way you can sort of maximize your dollars spent. If you have sites that are nearby each other, you don't need to put sensors on for both of them on this border. You put one sensor and it covers both sites. So it was just a way that we could save cost. But this was the other thing I wanted to point out is what it looked like to the operator here. So you see going along in time that this site was typically emitting something less than 5 kilograms per hour. And when this flare went out, it jumped to 300. And so it's a really unmistakable signal. And when you're working with the emission rate, it's really easy to trigger an alert off of that. Next thing I want to just talk about quickly is this Project Falcon that we did. And we did this just finished in October with the companies listed here. And the idea with Project Falcon was, well, from my perspective, there was 2 really burning questions. 1, how many sensors do you need on a site? And 2, where do you put them? And so this is a really great opportunity for us. So each of these operators over-instrumented the hell out of their site. So a site that we now know we would put 4 sensors on, for Project Falcon, we put 12 sensors on. And then the goal was to see when you use different subsets of that, how did it affect what we got? And so the first thing that we did was we looked at the height, because I'm sure you've all heard, everybody always asks this question, when tanks and flares are higher up than the SUFI sensor, are you going to see emissions? Because methane's lighter than air, blah, blah, blah. Now, theoretically, boundary layer theory would say that the buoyancy difference from methane and air is irrelevant. Turbulence is going to drive that mixing, and it's going to go to the surface as long as you're far enough downwind. But what happened with Project Falcon, we got to prove that. So we set up a tower with sensors at 3 heights, and we filtered our wind direction to when it was just coming from the tanks. And what did we find? Every sensor on the tower saw it 99% of the time. So the answer is, whether your sensor's at 6 feet or 20 feet, you're going to see the leaks. And so that was one really good result, because we were concerned about the additional cost of having to mount these on 20 or 30 foot poles. So that was sort of a good result from our perspective. The other one, and this one's a little hard to read. So what we decided to do with this is we start off, this 12 sensor line here is all 12 sensors on the site. And we assume that sees 100% of the emissions. And then we just take the different subsets. So we had 2 subsets of 6 sensors, and then we had 3 subsets of 4, 4 of 3 on down. And these little light gray lines are the single sensor subsets. And so the question was, how good did they do? And the 2 interesting results I'm going to mention. So one, we determined the sweet spot of 4 sensors, which meant spacing of 200 meters between them. But with 4 sensors, what we discovered is that the worst combination of 4 sensors saw about 40% of the emissions. So if you take a sample every 15 minutes, that means on average, you're going to find out about your leaks in about 30 minutes with 4 sensors, with the worst possible combination of 4 sensors. With the single sensors, that was the surprise to us. The best single sensor, so for example, if you're in the Permian with south winds and you put a single sensor on the north side of the site, you see about half the emissions. So really not very much different from the 4 sensors if you chose well with the single sensor, right? The best of the 4 sensors obviously is 75%. But what that meant to us is that when we had sites that weren't very productive and maybe weren't worth putting 4 sensors on, it was good to know that if you judiciously placed a single sensor, you're still going to find out, like, even if you're not quite perfect, you're still going to find out within a couple of hours on average that you have a problem. And a single sensor solution is super cost effective. So basically the bottom line of this is that 1 sensor is going to see all your leaks. It's just going to take more time. And so based on how critical those leaks are and how big the potential is, some sites may only be worth putting 1 sensor on. This is basically just final slide here, is kind of putting it all together, is when do you want to use each technology? And so from our perspective, if you're in an area where you can use continuous monitoring, and the one thing I didn't mention is that continuous monitoring is useless without real-time communications. And so if you don't have an area with cell service and you can't get on Wi-Fi or LoRaWAN, continuous monitoring ain't going to work. But if you can, that is by far the most cost-effective means of reducing methane. Moving down from there, if you want to survey like a large area, plane winds. If you want to get a really accurate methane intensity, that's where the drones are just unbeatable. They can do the best job of quantifying both complete site and individual component emissions. And then finally, if your goal is to go out and repair the small sources, after we've dealt with the super emitters, nothing can beat the camera for its ability to actually pinpoint. I think that's it. That's all I've got for y'all.